Hi, this is Kevin Trainer. I'd like to welcome you to my lecture on the uh, Chapter 8 of Murach's MySQL second edition. And Chapter 8 is entitled How to Work with Data Types. The objectives I'm going to leave for you. Uh, so, uh, there are a wide range of data types available within MySQL. Some of them are the standard data types that are part of SQL 92, and some of those are MySQL extensions. So let's see. I mean, there are a couple of considerations. One is a design consideration. Now, we're not yet at the point where we're designing tables. We're at the point where we're learning to use ones that have been designed by others. But generally speaking, if we wanted to make our data portable, such that we might decide to switch relational database products, then we'd probably want to keep our usage of proprietary data types to a minimum because the amount of effort to convert our data and then our code from one relational database product to another would be minimized. Okay, so we're going to do that. So the data types break down into categories, and we're going to talk about them kind of one at a time. Character, numeric, date and time, large object, and spatial. So here are the character types. Okay, there's your columns can have a fixed, you could say length, but you almost want to say width. Okay, so the field has a length and the column has a width, I guess. And if you use CHAR and then parentheses with a number of characters, then it has a fixed length or width, depending on how you want to think about it. And if you use VAR CHAR and then some integer in parentheses, then it can hold up to a character string of that length. So it could be 0 or it could be as long as the maximum. So a couple of issues here. Issue 1, how do you pronounce these words? Okay. Well, I'm going to tell you how a lot of people do it first because it's probably the main, they're in the majority. I don't happen to follow it. They say char and varchar. Well, that's kind of how it's spelled. Okay, so feel free to say char and varchar. You'd be in good company. I say char and varchar because they're characters. Okay. If you decide to side with me, you may be my friend, but you may be in the minority. Okay. So what we call them, you'll pick a side, and well, you can stick to it. Okay. Now let's look at the practicalities of it before we decide which one we might want to use. Okay. So, and I'm going to pronounce these things my way because I'm me, obviously. So the first example here, char 2, the original value, that would be the value that we coded on the insert, uppercase CA. Stored value, uppercase CA. Okay. and it's using 6 bytes. Okay. Now, in the second one, we have a char 10, right? We give the same values. It uses 30 bytes. So how long is it? Well, it's the max times 3. Well, why is that? Well, it's because we can store, in particular, we can store Unicode characters in these fields. And Unicode characters, even though they're a single glyph when we print them out, when they're encoded, can be up to 3 bytes long. All right. Or we can have a varchar 10, and we're going to say it's CA, and it's going to be 11 long. It's the length plus 1. Okay. Now, why would you want to go with a fixed length rather than a variable length? Well, one of the reasons you might want to go with a fixed length rather than a variable length is that that's the nature of the data. For instance, these state abbreviation codes are 2 characters long by definition. Okay, so if somebody should give you only 1 character or 0 characters, well, they're not proper values. Okay, so things that are a certain length by definition are great candidates for the fixed length char fields. By contrast, columns that can take on values that vary in length, like the spelled out name of a state, or the spelled out name of a city, or the spelled out title of a book, they're great candidates for varchar fields because of 2 reasons. One is that you, well, I'm sorry, whenever I say 2, it's always a different number. Primarily, it's in your interest to have kept track of how much of the field you're using up. For instance, if you want to take this value and you want to piece together a string of text, you don't want a lot of extra spaces in it. Okay, so if you put it into a varchar field, well then when you concatenate that string with other strings, well, it knows how long it is. Apart from that, you would have to do some further processing on it to make sure that your concatenated character string expression wasn't blown all full of error. So some things are kind of naturally varying in length, and some things are kind of naturally fixed in length. And this is a great reason to choose one or the other depending upon your circumstances. Some terms to know. Well, the Latin 1 character set, those are the characters for the most part that are used in the United States and Western Europe. There's a UTF-8 character set. UTF-8 is an encoding of the Unicode standard. And the UTF-8 character set is bigger than the Latin 1 character set. And years ago, when we would we'd install the MySQL product, we had to take an option to get to have the character set for the database be UTF-8. It's now become the default. And again, Unicode has the potential for one character being represented by up to 3 bytes. All right. So let's talk about numbers. Okay, and when we talk about numbers, one of the first things we're going to talk about are integers. So integers, as you remember from your math class long ago, are whole numbers. Okay, so why do we need so many integer types? Well, people sometimes like to save space. Okay, and people sometimes like to pick a type that helps to define the range of possible values for that column, right? The default int is 4 bytes long, and I think it holds up to a positive or negative approximately 2 billion. So that's pretty big. Okay. A big int is twice as big, so it's going to hold a really big integer. And then there's a medium int, there's a small int, and there's a tiny int. Now, if there's no special reason why your number should be really big, okay, like you need to account for values larger than 2 billion, then just use int. That makes a lot of sense. Okay. And in our current world, we're not overly concerned with storage space. So I'm disinclined to go use things that are smaller than a regular int. Although people will do it if you've got 50 million rows in a table, and there's got to be somebody somewhere with 50 million rows in a table. Of course, every byte you save is 50 million bytes, right? So that's a lot. But for our typical use, I think we're going to do well with ints. If we have a number that's always going to be small and we're concerned about the space our data is taking up, then we probably would want to at least entertain the idea of one of the smaller integer types. And if we've got potential values that we can foresee that are bigger than what would fall into a typical int type, then we might entertain the idea of a big int. So unsigned and ZEROFILL attributes. Okay, so when we define our columns, we have some extra attributes that we can specify that give that column special behavior. Okay? Now, when we're working on table design, we'll be thinking about why we would choose one of these attributes or not choose it. But now, when we're simply using tables that are already defined, it's important that we know how fields, how columns are going to behave based upon their definition. So if we have a normal int, it can hold positive and negative values just fine. So if you look at the original value, the value stored, the value displayed, they're all what you would think they would be. if we say that we have an unsigned int, that means that we expect it to only hold positive values. And if we try to store a negative original value, two things. One is it's not going to store it as a negative. And two is it's going to return an error when we go to do the insert or the update. Zero filling, okay, zero filling is going to cause our number to be padded with zeros on the left. And there are times when we want to do that. For instance, if we're trying to come up with serial numbers or account numbers or something like that, and we would like them to display with a certain number of digits. Okay. So zero filling is a kind of a way to control the format of this column when we display it. And here, this last one, int for zero fill, here's where we can say it's going to be zero filled and it's only going to be 4 digits long. I'm pleased to say that relational databases that conform to the SQL standard have a decimal fixed point number type that allow us to express anything we commonly express using this type are dollars and cents. Okay, so there are two kinds of numerical types. As soon as you begin to work with real numbers, numbers that are not just integers, that have a fractional part as well as an integer part, there are two ways to store them. One is in a fixed point number type like decimal, and the other is in a floating point number type like a double or float. The advantage of the floating point types is that they're more flexible. Okay, so you can use a double or a float to hold a very large value or a very small value. Doubles have twice the precision that floats have. So the number of accurate digits that they keep is twice as many for a double as for a float. The unfortunate thing is that they approximate the numbers that they're trying to represent by some amount of rounding. Now, if this doesn't bother a lot of people, especially people who are maybe engineers and scientists who are trying to come up with calculations that get the proper end value, because if you take a bunch of these things and you put them into a formula, the rounding errors tend to cancel each other out to a certain extent, and you wind up with a pretty reasonable answer. Not so with dollars and cents. With dollars and cents, you can wind up, we have a problem that I call off by a penny. So if in fact you take your dollars and cents and you represent them as one of the floating point types, and you control their format when you print them out so that you're only seeing the dollars and cents, you can have a sum of them that you print out in only dollars and cents by controlling the format on the output. Unfortunately, it can be off by a penny or two, depending upon how many rows you have. Now, the nice thing about decimals is that they are within the number of digits that they have, they are exact. And so if you look down here at the bottom of the slide where we have the first three examples are dollars and cents, and we define the column as decimal 9-2. So that means 9 digits overall, 2 to the right of the decimal point. Well, this is just perfect for dollars and cents. They're signed values, right? And we always keep 2 decimal digits of accuracy. So if we store 1.2, we get 120. If we store 1, 2, 3, 4, 5, 6, 7, 8, 9, we get that. If we store a negative version of the same thing, we get that. These are beautiful for accounting-oriented applications where people get upset if you start losing pennies. Okay, so for commercially oriented applications, they are perfect. They're also good for representing numbers that have a fractional part where you want to control the accuracy. So here is the last of the decimal, 18 digits, 9 to the right of the decimal point. And so it's going to keep things that are that accurate. And then, of course, at the bottom we have the double and the float. And the doubles, reasonably good. You can see that you have 9 digits of precision, and that's fine. So we're not losing any digits to rounding. But if you look at the float, we are losing some digits to rounding. And floats are, unless you're dealing with small amounts, if you're using numbers that are very large or very small, floats are prone to errors and not recommended. So terms to know: a real number, that's a number with a fractional part. Precision, that's the number of digits of accuracy that you're keeping. So if we say decimal 9,2, the precision is 9. Okay. The scale is the digits to the right of the decimal point. So in 9,2, the scale is 2. An exact numeric type would be a type like the decimal or the integer, where we're not rounding and approximating it. We would contrast that with a floating point type, which would be either a double, which we'd recommend, or a float, which we would not recommend. And those would both be approximate numeric types. One of the things that I often say that to be humorous is that you could use doubles to do the calculation to get a spacecraft to Mars, but I'm not going to recommend it as a way to keep it to balance your checking account. Okay? Because of the potential off by a penny problem. Okay, date and time types. So here in MySQL, we've got the following options. Date, time, datetime, timestamp, and year. Okay? Let's see if we can talk about that. Okay, so let me bang up. Um, these slides are kind of thin here. Apologize for that. When we store dates in SQL, we typically store them with the date and the time. Okay, so we typically store a date time. There's also a thing called a timestamp. Okay, and a timestamp is interesting because it's a type that we can use to automatically have the time inserted into a column when we insert a row. Unfortunately, the timestamp as a data type in SQL has the problem that I forget the year, but it has a problem like it doesn't represent years well after 2037, 2035. Something is becoming a little too close to recommend that we use it. So, how does MySQL interpret literals for date time? And I just want to point out here, all the literal values that we've seen in the slides for this chapter are enclosed in single quotes or apostrophes. And we've had some discussion. We had, I think, a really interesting discussion in our office hours session earlier this week, in which somebody said, well, I think there are rules for when you use apostrophes and when you use double quotes. And I happen to say, well, no, don't worry about that. You can use either. And for the most part, in MySQL, the way it's currently configured, you can pretty much use either. Okay? And that's because when we install the product, the option that allows you to use them fairly interchangeably is turned on. Now, if you happen to be using an installation where that's not turned on, or you happen to be using some other product, it turns out that there is a sensitivity in some products, in some of the configuration, to when you use apostrophes and when you use double quotes. And the conservative thing to do is to use the apostrophes around these literal values. These would be the values that you were using in an insert, or they'd be the values that you would be expressing as the value in the expression in a where clause or a having clause. Okay, and the expressions that represent some kind of object in the database, for instance, something like a column alias, they traditionally have been in double quotes. So that's the conservative way to code them. All right, in our current environment within our class, it doesn't really matter, but it might matter to you if you want to write code that's compatible with a number of products, including products that are not MySQL. Okay. Okay, so let's look at this. We have a date column, and we are storing 2014-08-15, and we get that value in as we see it. As you can see in the second line here, we don't have to prefix the 8 with a 0. It's smart enough to allow us to do that. We can just have the 2-year year, although that's probably not a good practice. It hasn't been a good practice since 1999, so we probably want to avoid that. We could have we could have the date without any punctuation, so that works. Interestingly enough, we can have the date as an integer literal, and that seems to work well, but it does require that we put the zeros before the we have to go to 2014 and then 0815, not just 815. You can see the next line where we've got the periods. Okay. Notice that's inside of some kind of quote marks. We can use the next where we're using some kind of slashes. And again, I don't think that using a 2-digit year as your input is a good practice. You can use the next one, 8:15:14. You can try to use that, but that's not going to work. Okay. Probably because we don't have the year first. Okay. So it's year, month, day, kind of the way the Europeans would do it. Okay. And whatever we express has to conform to the rules for dates. So if we try, if in fact we get the string in the right order, but we try to express the 31st of February, of course, that's going to generate an error. Here's how MySQL interprets date-time literals. Okay. So in terms of time, 7:32 is going to be 07:32. Okay, so that's going to be in the morning. 19:32:11 is going to be 19:32:11. That's going to be in the evening. We could express the same string without the colons and get the same value. We could express the same digits as an integer and get the same value. Okay. And the last example here is just no matter how you express it, you have to express proper time. So you can't say that you want 61 minutes because that is an improper time expression. So here's a literal value, okay? Let's say we have a datetime field, or we have a datetime column or a timestamp column, right? And we want to populate it. If we provide the date and the time, it's going to store it as the date and the time. If we provide only the date, it's going to store the date and leave all zeros for the time. Okay, so now we've come to some of the more exotic types, enums and sets. And I've got a couple things to say about them. One is that they're kind of neat, and two is that I don't recommend them. Okay, so we have an enum and a set. So let's look at how enums work. Enum is short for enumeration, and these are very popular in programming languages. Modern programming languages are called enumerations, and what they do is that they add some structure to a field that otherwise could for instance, be just defined as a character field. Okay, so let's look at what we have right here. We have yes, no, maybe. Okay, and those are the three values that are part of the enum. So if we say the value is yes, well, that's in the list. It goes in. If we try to insert a no, no goes in. If we try to insert a maybe, maybe goes in. If we try to insert any other word like possibly, we don't get any value in there. It's like it's the empty string. Okay, so it controls the values. Okay. Could we control the values better with another table that we have a relationship to? Yeah, I think we could. Okay, and that's the reason why I don't particularly like enums. Okay, because they don't really add anything we couldn't have done with normal relational database capabilities. The enum type is implemented in MySQL. It hasn't been implemented in either all of or most of the other SQL implementations. And so for the reason that it's not particularly relational database like, okay, and because we could replace it with a lookup table, and so we would have a table of valid values, yes, no, maybe, and then we would put they would have primary keys 1, 2, 3, and then we would use a foreign key on the end that where we wanted to use that value, and then the foreign key would point at either yes or no or maybe. The thing I like about that, which is the traditional approach in relational databases, is that what if we all of a sudden want to entertain other valid values? Well, we don't have to redefine anything at all. We just go to the table that we're pointing to and we make further entries. And so the extensibility of that, I think, is much greater than the enum. So that's one of the reasons why I don't really like enums. Actually, those are several of the reasons why I don't really like enums. Sets are a little different, and they're kind of neat. Sets are based upon set theory. Okay, so in set theory, the members of a set only occur once. Okay, so when we say that we have the set of pepperoni, mushrooms, and olives, okay, then pepperoni can only occur once, mushroom can only occur once, olives can only occur once. So what we say here is that we can say that a particular value is that it only has the pepperoni part, okay? We don't have mushrooms or olives here. It only has the mushrooms part, okay? Now, here's the third example here, pepperoni and bacon. Well, it only has the pepperoni part. And then olives and pepperoni. Yeah, it has pepperoni and olives, and you can see that they show up in the value that gets put into the column, that they show up in the order that they're defined in the set. I think this is a cool idea. There are set types in more than just MySQL. For instance, I was just looking at the capability in Microsoft SQL Server So, but this is not a standard type. And this isn't really a relational database way to solve this problem. Um, there's a way to solve this problem that's more flexible using foreign keys and tables. Now, in this case where you can have multiple values, um, uh, you need to add two tables. Okay, so and this kind of breaks the rules of well-formed relational databases in that um, relational databases that meet the rules for normalization are not supposed to have what we call repeating columns. And so storing more than one value in the same column really breaks that. Okay. So in the last analysis, I think that both SET and ENUM are kind of subversive ideas when compared to the sort of theoretical underpinnings of relational databases. And while I think they're cool, I'm not recommending them. Large objects. Okay. Now, large objects weren't always a part of SQL, but it, when SQL became a very popular standard for relational databases, it was along the time when we realized we might want to store things in a database that we never really thought we were going to before. Okay? Um, and these are documents, um, images, those kinds of things. Uh, Audio files, executable program files. So these things can get big, okay? And why would we want to keep these? Well, we might want to keep these if we're using the database as some kind of a repository, okay? So we want to use it as a repository of documents. So we want to have a table that, for the most part, just holds the document, or maybe the document, a little bit of the metadata for the document. These large objects become a great way to do it. Okay, so terms to know down at the bottom: blob, binary large object. This would be something like an image file, a sound file, an executable file. Or clob, character large objects. This would be something like a document, a paragraph, a list. Okay? So we have a lot of possibilities here. Okay? We have a long blob, a medium blob, a tiny blob. And one can be bigger than the next. Okay? And so the number of bytes that they take up are bigger the longer that they get, because they need something. They need a field associated with the payload that says how long the payload is. And the longer the payload is, the bigger that field has to be. And then with text, we have the same thing: large text, medium text, text, and tiny text. Again, the text is the payload, and how long is that? Well, if you want it to be really, really long, then you want to use the large text type. Okay, and that uses up a little more space, but it gives you more flexibility. Now, we're not at the point where we're designing our tables yet. So a lot of the discussion we've had in the chapter has kind of talked about that, and we're going to file that away and keep that information until we get to, I think, chapter 10. Okay? But we are at the point where we need to get data into and out of the database, and what we want to know is how can we do tricks with the SQL features that allow us to get the data into and out of the database in the most favorable way. So here's the situation, the first one on slide 16. We want to implicitly convert a data that's a number to a string. Okay? So how could we do this? Well, we can take any number like invoice total, and we can concatenate it with some string part. And the rule is that it will turn the number into a string and combine them. So if you look at the result set here, and it's a little bit hard to see, so why don't we make that a little bit bigger. Okay, if you look at the result set there, we have the $, and then we have the string, and see how they're left justified. So this is definitely a string, right? This is not an amount. All right. So let's look at a couple more. Sorry, I have to jump back. All right, so now we're going to go back. The second one is to convert a string to a number. Okay, so we have an expression here in our select clause. The second expression has an integer divided by a character field. Okay, and it will, in this case, try to convert this character field to a number and do the division to get us a result. Okay, and that's what we got here in the second column. The next example, we're implicitly converting a date to a number. Okay, well, how do we do that? Well, we're using a date field, invoice date, and we're adding 1 to it, and it just so happens that the rules say that if you do that, then it converts the date to a number. It's converting it to its sort of integer form, and it's adding 1. Okay, so there are some tricks to getting things in the form that you'd like to have them. All right, that makes sense. Or you can do it more explicitly. Okay, so the tricks that we just saw, they all happen implicitly. Okay, having to do with the rules of implicit conversions. Okay, how about if we wanted to do it explicitly? 2 choices, cast and convert. Okay, so we can say cast expression as type, or we can say convert expression type. Okay, these are very similar and competing capabilities. Okay, for cast types, you can use in these functions. Char n, date, datetime, time, signed, unsigned, decimal. Okay, let's see the same thing done in 2 alternative ways. First with a cast, and then with a convert. So first the cast. We are selecting invoice ID, invoice date, invoice total, And then we want to cast invoice date as char 10, and we're going to call that char date. And we're going to cast invoice total as signed, and we're going to call that integer total. Okay? So when we take the invoice total, okay, it starts out as a decimal. Okay? So it's got fractional parts. And so when we cast it as a signed, we are casting it to a signed integer. Okay? So we're getting the results. So we're getting a character date, and we're getting a signed integer. Or, in the alternative, we could use the convert function. So we say, with the first of the fields, convert invoice date, char 10, convert invoice total, signed, and then we get the same results. What I like about the convert is that the syntax is a little more like your typical function, in that it has argument, comma, argument. Whereas up in cast, we have argument, and we have this as operator, and then we have this other argument. So I like to convert over the cast because it has a more modern syntax. Okay, but as you can see, we got the same work done in two alternative ways. We can also use the format and the char functions. Okay, so let's look at the format. Okay, so we're saying that we want to format this numeric value, comma, 2 decimal places. Okay, typically we would not be using a literal value. We would be using the name of a column. Okay, and that would be a column that, say, either had more decimal places. Okay, say it was a decimal and it had more decimal places, or fewer decimal places. So we wanted to have it show as 2 decimal places. Or we could also do that if it were a double, if it were a floating point column. Here we're saying we're taking a 2-digit decimal. We want 4 digits to the right of the decimal point, so it's going to pad out the zeros. And here we have a 2-digit decimal. We'd like to format it at 0 decimal digits, and so we're getting a whole number. Note that we are getting rounding. Okay. Okay, because it's 1, 2, 3, 4.56, 5, 6, we round up, 1, 2, 3, 5. Okay, so with this formatting, we get implicit rounding. Let's look at the char function. What if we want to put characters into the output? Now these are things, there are times when we want to control the output to get it into a particular format. In this case here, if you look at the bottom of the slide, we're trying to get a classic 3-line address. Okay, so what are the characters that we can insert into the output? Well, we can insert a char 9. Okay, this is the character code. This is the decimal character code for tab. A char 10 is the line feed. A char 13 is a carriage return. And so we're saying that we want the vendor name, and then we want char 1310, carriage return line feed, and then we want the address, and then we want char 1310, carriage return line feed. And so that's how we got that done. Okay? So by putting those there, it creates a literal value that's the sequence of the 13th character, then the 10th. And that's how we got these two carriage returns. Okay? Now, is this typical that you would want to do this kind of formatting in your query? No, not typical for me, but there's the capability. Absolutely. Okay, so that's it for us here. So the takeaways for this are, one, begin to get the idea of what the kind of what the data types are for columns, because in a handful of chapters we're going to be designing tables and we're going to have to choose them. So that's it. In the meantime, to understand how to read the definitions for columns and how to have the right expectations of what's going to come from the columns in our queries, and then some tricks to get things into the right form for us as we use our queries. So giving you all that to think about, I'm going to say bye until next time. Bye-bye.